The next layer of the topic that we were going to cover, that I didn't start this Tuesday because we had like 7 minutes left, and I can launch into this, 7 minutes left. You can find higher order derivatives with multivariable functions, just like you can find higher order derivatives with a single input function. The notation, again, notation is just notation. It's, it's like all parts of language. Symbols get made up to represent something, and you try to become familiar with as many symbols as you can. I mean, for example, it's probably helpful to know how to say hello in as many languages as you can, So there's lots of different symbols that represent the idea of the higher order derivative. So, for example, we were introduced on Tuesday to the idea of writing a little subscript to indicate which variable you're using as the variable. Because remember, if you're taking a partial derivative, you're treating one of the variables as the variable, and then the other variables get treated as if they are constants. So if I took the derivative with respect to x, meaning x is the variable, and then I took the derivative again, so I'm finding the second derivative with respect to x, I could use any of the notations that are in that front row of information. So f of x, parenthesis of x, and then you could get rid of the parentheses if you want to and just write f sub xx. There's also that partial symbol that I introduced you to. Again, it looks like a Greek letter, but it's actually not one of the Greek letters. And so this means I'm finding the partial derivative with respect to x, and then I find the partial derivative again with respect to x. If you put that together, you could express it like it is here. Remember that the function, if z is actually the variable that's representing the output, you could replace the f with z. Okay, so I know you guys understand the idea of a second derivative from Calc 1. What we need to do now is get more practice when you're trying to hold other variables as if they're constants and focus on just one variable. You can also take the derivative with respect to x and then switch modes and treat y like it's the variable and make x the constant. If you do so, you could express that idea like I have it here. You could get rid of the parentheses and express it like I have it here. You could express it like I have here. So I found the partial with respect to x, and then I took the partial of that with respect to y, meaning I'm switching who's that variable. If you get rid of the parentheses from this notation, it looks like this, where the 2 is indicating a second derivative, but notice first I took the derivative with respect to x, then I took the derivative with respect to y. Notice these are reversed from over here. Okay, and the reason why is this one, we read it as, I took the derivative with respect to x, and then I took the derivative with respect to y. Whereas due to how we were sort of distributing this to this, if you then remove the parentheses, the x and y are reversed in the order that you use. Again, it's not that big of a deal, but I'm just pointing it out to reduce confusion later. And then the second derivative with respect to y would have similar notation as with respect to x, and then I could take the derivative with respect to y and then switch modes. All right, so let us work through the above partial derivatives with our first, remember this was the function, the first function we had. I think it's the first function we had. Yeah, there was our, this is our terrain we'll kind of discuss some interpretations of it, all right? So we're finding the second derivative with respect to x first, so I remember our first derivatives were kind of messy. So f sub x, we have denominator times the derivative of the numerator. See, we're holding x as the variable, y is the constant, so this is the denominator just listed, okay, I'm doing the quotient rule. Denominator times derivative of the numerator minus the numerator times the derivative of the denominator. The derivative of e is itself, but then we have to use chain rule. So the derivative of that exponent with respect to x will be 1x to the first power. Again, the 0.8y squared is a constant. And then we want that over our denominator squared. Okay, so cleaning that up. Again, you guys should already have what I just did in your notes. I just kind of remember reviewing it. So we were able to factor out a 4y and an e to the 0.5x squared plus 0.8y squared, and 1 minus x squared times e to the 0.5x squared plus 0.8y squared. And okay, so that,
What are you supposed to? Yeah, the x squared times e to the 0.5 x squared plus
It should just be
0.8y
x.
squared. That shouldn't be there, right?
Yeah, it should just be an x squared.
hang on. Is, okay, denominator, derivative of the numerator would be 4y minus the numerator, and the derivative of the denominator would be itself times the derivative of 0.5x squared, which would be 1x. So then, both of them have a 4. Both of them have a y. Both of them have an e to the 0.5x squared plus 0.8y squared. So I factored that out. This would give me a 1. And then over here, I have an x here, and I have an x there. And then, okay, I factored that out. All right, okay, I'm sorry, I see what you guys are saying. I think through it myself. All right, so we get 4y times 1 minus x squared over e to the 0.5x squared plus 0.8y squared. So again, because we're going to do something with it, we're finding a second derivative. It was worthwhile to clean it up. So I know, in Calc 1, when you first learn derivatives, I know the question always comes up of, well, do we have to clean it up? And it's honestly, it's a gray area. There's sort of an art to cleaning things up. The more problems you do, the more you realize what are useful ways to clean things up and why you want to clean things up. If we were going to find the second derivative, though, it certainly is going to be a lot easier to mess with the final thing I have on the board than what we first started with, okay? So my second derivative with respect to x will be, I'll just do the quotient rule again. Denominator times the derivative of the numerator, and we are treating y as a constant because I'm still treating x as the variables. The 4y times 1 is a constant, but the 4y times minus x squared will be a coefficient of x squared. Okay, so denominator and then the derivative of the numerator should just be what I had there. Minus the numerator times the derivative, oh shoot, well, it may just fit. Times another x. Okay, again, the denominator, because we were able to cancel out that one factor, is e to that function, and then the derivative of the function that's plugged in e, again, is x, and then it's over our denominator squared again. Alright, so factoring, they both have the e to the 0.5x squared plus 0.8y squared, and they also both have a 4, and they have a y, and they have an x. So here, I'm left with a negative 2. And then this one, I am left with a negative 1 minus x squared. That's all. I'll step back and double check this a second. Okay, so 4 comes out, y comes out, x comes out, anything comes out. So the only thing left in the front term was negative 2, and the only thing left in the second term is the 1 minus x. And this cancels one of these. And so cleaning it up, I get negative 8xy minus 4xy. If you had wanted to leave the numerator factored, you could too. I probably would have at least factored the extra negative out. All right, so that's just practice, keeping the idea in mind that one variable actually is being treated as a variable, the other one is being treated as a constant. And again, it's just a mindset you have to kind of get in.